A very good day to Doctor and my fellow friends. My name is Samuel Ng Jian Hao. I'm from SKEE1073 Electronic Devices and Circuits, Section 1, Group 10, and my group members are Tan Zijian and Muhammad RAFIQ bin Suradi. I'll be representing Group 10 for this video presentation on Assignment 1, which is about converting AC to DC power supply. So today I'll be explaining our assignment on converting AC to DC power supply using a full wave bridge rectifier, which we have built and tested using Tinkercad. So without further ado, now we'll move to the first stage, which is a basic full wave bridge rectifier. Okay, so this is stage 1, which is the basic full wave bridge rectifier. So I will start simulation to prove that our rectifier is working. Okay, so as you can see, our rectifier is working. In order to set up this rectifier, we would first of all need to have a AC voltage source, which is this. We need to set the frequency of the AC voltage source to 50 Hz and the voltage to be 10 volts. After that, we need to configure 4 diodes in a diamond shape configuration, as you can see here. We name the diodes as diode 1, diode 2, diode 3, and diode 4. And of course, we also need to have a load resistor, and we set the load resistor as 1 kilo ohm. So the AC current is divided into the positive half cycle and negative half cycle. So during the positive half cycle of the AC current input, current will only flow through diode D1 and diode D2 because only both of these diodes are in forward bias. So diode 3 and diode 4 are in reverse bias, so no current will flow through them during the positive half cycle. So the function of the diodes is to actually direct the current flow in such a way that both halves of the AC waveform are redirected to the same polarity across the load. This means during each half cycle of the AC input, 2 diodes conduct and allow current to pass through the load in the same direction. So as you can see at this oscilloscope, it shows that the AC input is showing a shape of the graph which shows the positive cycle and the negative cycle. Okay, and for the output oscilloscope, the output waveform displays as a series of positive pulses only. Instead of alternating between positive and negative like the input AC signal I mentioned earlier, the waveform now only appears on the positive side, as you can see here. So we have also calculated the output voltage using KVL, as you can see here, which is 8.6. So that means the value here is 8.6 if we follow our calculation previously. So however, it's important to note that this output is still not pure DC, as it still contains significant ripples and varies between high and low voltage levels throughout the cycle. While it is a step towards DC, this type of output is not yet suitable for powering most electronic devices due to its instability. So let's move on to stage 2. Okay, so now this is the stage 2, which is the bridge rectifier with a capacitor as the filter. So again, I will start simulation to prove our rectifier is working. Okay, so as you can see, our rectifier is working. So what's the difference between this stage and the previous stage is that we have added a capacitor here. As you can see, we set the capacitor value as 50 microfarad, and other components in the circuit remains the same. We just add the capacitor as a filter. Okay, so to improve the quality of the output, we added a capacitor in parallel with the load resistor. Okay, the capacitor acts as a filter. When the voltage from the rectifier increases, the capacitor charges up and stores energy. When the voltage drops, the capacitor discharges slowly, helping to maintain the output voltage for longer periods and fill in the gaps between the pulses. Okay, to prove that, let's look at the output oscilloscope here. So looking at the oscilloscope output for this stage, the waveform is noticeably smoother compared to stage 1, right? So instead of sharp pointed peaks like in the first stage, the waveform now resembles a series of rounded humps depending on the capacitor value. Okay. Similarly, for this stage, we also do some calculations for this stage. We calculate the VRPP, which is 1.72. And from the calculation, we also get the Vmax, which is 8.6 volts, and V minimum, which is 6.88 volts. Okay, so as you can see here, the Vmax and Vmin is here. So this indicates a significant reduction in voltage ripple compared to the first stage, resulting in a more stable DC output. While it still isn't perfectly flat, this kind of output is still better than the output we got on the first stage. Okay, so to further improve the DC output, let's move to stage 3. So finally, we have reached stage 3. Okay, this stage is the complete rectifier with capacitor and Zener diode. Okay, so for this, I will also start simulation to prove our rectifier is working. So start simulation. Okay, so as you can see, our rectifier is working. Okay, so what is the difference between this stage and the previous stage? So in this stage, as you can see, we connected a Zener diode here. Okay, so this Zener diode is crucial at this stage because it acts as a voltage regulator. Okay, at stage 3, we connect this Zener diode in the full wave bridge rectifier. Okay, and the Zener diode is connected in reverse bias, as you can see here. Furthermore, the Zener diode is connected in series with the current limiting resistor and connected in parallel with the capacitor. Okay, there's also a resistor here which is connected parallel to the Zener diode, okay, for voltage regulation to occur. Okay, the capacitor here acts as a filter, okay, and on the other hand, the Zener diode here acts as a voltage regulator in this full wave bridge rectifier. The capacitor is connected in parallel with the Zener diode to ensure that the Zener diode maintains a constant voltage across the load and is able to regulate the circuit's output voltage. Moreover, the output voltage can be further stabilized by connecting the Zener diode in parallel with the load resistor, as you can see here. Okay. With the Zener diode in place, the circuit not only smoothens the waveform using the capacitor, but it also clamps the output voltage to a fixed level defined by the Zener diode's breakdown voltage, depending on the diode use. So as you can see at the final output oscilloscope here, you can see the waveform appears almost completely flat, which shows that the output voltage is both smooth and regulated. Okay, so this is the kind of output that we would like to expect for converting AC to DC power supply. Okay, so similarly for this stage, we have also did some calculations to calculate the Zener current, the range for Zener current, which is the minimum is 5.74 milliamperes and the maximum is 6.6 milliamperes for voltage regulation to occur. Okay, so this is the final and complete rectifier that my group has tested in Tinkercad, and it is working, as you can see from the oscilloscope here. Okay, so that's all for stage 3. So now I will do a conclusion for our video presentation for assignment 1. So in conclusion, this simulation clearly shows the progressive steps involved in converting AC to DC power. So in the first stage, as you can see just now, we have mentioned the first stage uses a bridge rectifier to convert AC waveform into pulsating DC. Okay, and moving on to the second stage, as you can see here, we add a capacitor as to filter out voltage ripples and deliver a smoother DC output signal. And the last and final stage, we further improve the output by stabilizing the voltage using a Zener diode, ensuring that it remains constant even if the input fluctuates. That's all from Group 10. Thank you for watching our video presentation.